Hey everyone, today we're going to be talking about equilibrium and how concurrent forces can produce equilibrium. In order to figure that out, we got to figure out the resultant of concurrent forces. And we had talked about this previously, but the vector sum of two or more concurrent forces that are acting on an object are what we call the net force, which we represent, and we'll see a lot of this notation, as F sub net. Make that a little bit clearer. F sub nets. So if we find the resultant of concurrent forces, that resultant would be known as F net. So we're going to look at today how we can produce equilibrium between F net and another force. So if the net force that's acting on an object, or the vector sum of all the concurrent forces acting on an object, is 0, then the object is considered to be in equilibrium, which, if you remember from chemistry, is a state of balance. Can be static, can be dynamic. And an object at rest, since it's at rest, is said to be in static equilibrium. Static since it is not moving. So if we have a force that is equal in magnitude, but is opposite in direction to the resultant of concurrent forces, or to our net force, this is going to produce equilibrium. And I'll show you an example of what I mean by this. If we consider two forces, F1 and F2, F1 being 4.5 newtons directed north, and F2 being 6 newtons directed west, which force will produce equilibrium of the resultant? So if we consider these two forces, I'll start these from point P. I'm going to give myself a little more room there. We start these from point P. F1 is equal to 4.5 newtons. And F2 is 6.0 newtons, and that's directed west. We will assume that this is drawn to scale so that we can accurately draw our resultant. So if we connect these forces head to tail, this would be F1 prime as we translate that over there. So we connect F1 and F2 head to tail. Our resultant will be drawn from the tail of our first vector to the head of our final vector. Only that we're a little bit more straight. Let me see if I can try something here. And our resultant, that looks a whole heck of a lot better. Should do that for all of my drawings. Our resultant here is going to give us our net force. So now we can use a little bit of math here with our right triangle to figure out the resultant. So we have 4.5 newtons. Now that I'm looking at this, those were not squared, those were, I don't know what you call that, squared there. It's 4.5 newtons squared plus 6.0 newtons squared equals our resultant squared. This comes out to 56.25 newtons squared. This is equal to our resultant squared. We'll take the square root of both. Our resultant comes out to be 7.5 newtons. and that is directed north of west. So we got a resultant. So what we want to look for now is the force to produce equilibrium. We want to figure out what that force is going to be. And that force is going to be equal in magnitude to R, but opposite in direction to R. It's essentially going to cancel out our resultant and put our forces, or our net force there, into equilibrium. So we're going to have an R, and it's still there, that's equal in magnitude but opposite in direction. This would also be 7.5 newtons, but it's opposite in direction. And the opposite north of west would be southeast. So we need a 7.5 Newton force directed south of east in order to produce equilibrium. Last thing we'll take a look at for today is what we call a free body diagram. And a free body diagram is a sketch, could also be a scale drawing. Kind of depends on what we're using it for. And it's going to show us all the forces that are acting concurrently on an object. And this will allow us to kind of evaluate and determine net force, make sure we're considering all forces acting on an object. Gives us a nice visual representation of what's happening here. So I'm going to do a awesome sketch here. This one will probably not be to scale, although it will be represented to scale. We'll consider it as being to scale. I'm going to use a ruler for this because I think if I try and do this without the ruler, it might look kind of bad. Let's say that that looks pretty good. If we consider two different forces here, F2 directed along this line and F1 directed along this line, we'll call this a rod, and here we're going to have a cable. And these two pieces of equipment are going to be used to support a sign for my new business, DiRienzo's Donuts. So that sign is being held up by this solid rod being extended away from the building. My storefront with delicious donuts. Maybe I should have called it DiRienzo's Delicious Donuts for next time. So the sign's being suspended here from the rod and the cable. And there is one force we're missing here, which we'll add in, which is the weight of the sign. which we also call F sub G. Now if we do a little sketch of this and do a little vector math, we have F1 directed in this direction, F2 directed along this line. Our resultant can be drawn here. And the resultant is actually the inverse of our weight. So the weight is represented downwards, so that's F sub G, which is equal in magnitude but opposite in direction to the resultant of the force of the rod and the cable. So this diagram would be used to show all the forces acting on the D'Arienzo's donut sign. A Newton, as we start to get into this more, is represented as a kilogram times a meter over a second squared. We'll be referring to that rather often. So in this free body diagram, we have two forces, two concurrent forces working to hold up a sign, and a third force, our weight, being directed downwards, opposing the resultant force from the rod and the cable. I'll leave you with a little joke for today. Where did the vampire college student go clothes shopping? Forever 21. Have a great day.